Okay, so if I have done everything right, when I run this, it should print 100 maths. Yeah, 101. It's just that easy. It's just that easy. Let's make a programming language. Why not? So, I've had this idea floating around in my head ever since I watched Tsoding make Porth. And if you've never seen Tsoding and you don't know what Porth is, you're in for a treat. Let's see if I can get it up on GitHub. So, oh, GitLab, sorry. So, it's a programming language that is stack-based, yeah, concatenative, which is basically every operation operates on a stack. So if you were to, put the number 10, that pushes 10 onto the stack. And then if you put 5, that pushes 5 onto the stack. And then if you put plus, that then pops the two numbers off the top of the stack, adds them together, and then pushes the result onto the stack, 15. I wonder if he has any examples. Yeah, here you go. So you can see here. So this is how you define a main function in Porth. So you push 34, 35, you add them together, so it pushes 69 onto the stack, and then you print it, which pops it off the stack. And from memory, and you can see there, it prints 69. And from memory, a valid Porth program must end with an empty stack. Although I guess that's kind of implied by the signature of the main function. I think he has some other examples somewhere where you can have functions that return values, and because interestingly, it is a stack, you can return as many values as you want because the signature of a function, here you go, is defined by what is on the stack before and what is on the stack after you call the function. So for these are built-ins, but for dupe, it takes in anything. So it's kind of like I think this is like Haskell, where lowercase is like a generic. So it takes in a generic and it pushes two of the generic on the stack. Swap takes in two generics that could be different and then pushes them back on in a different order. So that's Porth, and Porth is I guess imperative. I'm a bit flaky on the actual definition of imperative, but basically it's not functional. And so I had this idea, and it's very much not a original idea, but I don't like to look up when I have an idea for something that I want to program, because A, someone's going to have done it better than me, and that's just going to kill my enthusiasm. And then B, it also is just spoilers for how to solve the problem that I'm trying to solve, because I'm doing this for fun. This isn't going to be the C killer. This is a silly toy language that nobody is going to use. So what do I imagine this language to look like? So if let's make a resources, and let's make a file. I don't really know what to call this language. I've toyed with the idea of do as kind of like a a joke, because like Go is a horrendously SEO unoptimized name for a language, so do is even worse. And I imagine one of the operators being do, the same way that Go has the Go keyword. So we'll get to that. So I'll show you what do does. So let's just do foo.do. So what does this language look like? Well, so it's very similar to Porth, where you're pushing values onto a stack. And with Porth, those are integers, strings, booleans, just your types, whatever. As far as I remember, there's no concept of like arrays. Although maybe there is, but it's like implemented through pointers. So it's very much like C in terms of like its capabilities. So I want to go one further and push whole lists onto a stack. So you would do that. I'm thinking like this. So this is one operation, and what that does is it pushes a list of 5 numbers, or 5 integers onto the stack, all in one go. And then, and that's denoted by the square brackets. And then if you use round brackets, you then start to push a function onto the stack. So if I were to say dupe star, so if we were in Porth land, so let's forget that for a second, and we were to say 5 dupe star print, what that's going to do is it's going to push 5 onto the stack, and then it's going to duplicate it, so it's going to push another 5 onto the stack, and then it's going to multiply them, so 5 times 5 is going to push 25 onto the stack. So this is squaring. So what I've done is I've pushed... my monitor's just turned off. One moment. One of my cables hit the light. So what I've done is I've just pushed the function onto the stack that squares a number. And in my syntax, not syntax, but like style, you got to imagine this is like method chaining. So we have a list of integers, and we have a function that takes in an integer and returns an integer. So this function pushes an integer, pops an integer, and then pushes another integer. So you can imagine this as a function of integer to integer. So with that, I can map this list with this function. And this is all stack based. So map is going to pop off a function that, if we go back to our generics, it's a function that takes, it pops off a function that takes an A and returns a B. That's the signature of a map. So this is what this is, where A and B are just, they both happen to be integer, but this could be, it could be 5 greater. And so that would push, that would just replace it with a list of falses, but that then pops an integer and pushes a boolean. But I'm just going to go with this. So map would then pop a function and pop a list, and it would apply the function to every element of the list. So then that pushes 1, 4, 9, 16, 25. And then we do this. So do, I'm imagining, is the function, like, really this would be like apply or do is different, I think. Apply, yeah, we'll get to do. Apply instead pops off a function that consumes anything and returns nothing. So print would go from A to nothing. Just pops off whatever's on the stack. And it takes a list of something that matches the type that it pops. And for each, I guess it's like for each, most. So you could do apply, you could do for each. And so that would then print 1, 4, 9, 16, 25. And I don't know, this idea interested me, because like on the surface it feels easy to do. Like this doesn't feel like it's that groundbreaking. But the more I thought about it, the more it kind of got more complicated, because I want this to be type checked the same way Porth is. That was something very interesting about the Porth streams that Tsoding did, where throughout the compilation of the program, by the way, I am going to start with just an interpreter, because compiling this is that's quite an ordeal. So I'm just going to start with interpreting it, which is going to be much easier. But throughout that process, you will kind of have a type stack in your compiler, and as you're interpreting, or as you're like walking the tree of the program, you're going to be building up this type stack, and then making sure that, you know, if I encounter a plus, I need to make sure that the next two elements on the type stack are integers, or, you know, something that can be applied with plus. If not, then that is a compilation error. That's very interesting. But it gets really tricky with these quoted functions, because you kind of can't maintain just one type stack, because as soon as you go into this function, you don't have a type stack anymore, and you have to like start anew. And dupe, normally, if we were in Porthland, or, you know, if we were outside of a quoted function, if I did 5 dupe, that is fine, because as I'm compiling this, I will see, oh, I do have something on the stack, so I will just copy that and I will push 2 of those onto the type stack. But if you have to throw away your type stack when you go into a function, because remember, this doesn't call the function until something invokes it. So I could just as easily have written these in the other order. And this wouldn't compile, right? Because you can't map a function with a list. But what I could do is I could type swap before, and swap, as we saw, is a function that takes an A and a B, and then pops them off, and then pushes B, and then pushes A. So as this gets interpreted, you don't know at compile time what this is going to get applied to. You kind of have to interpret the whole program before you know what's going to happen. So this has to resolve to a generic function. And that feels kind of interesting, to have to type check this. So that's what we're going to be doing. I have no idea how. Yeah, let's put this back. This is probably not going to be the first. Oh, come on! How am I doing this so badly? There we go. This is probably not going to be my first do program that we interpret. I think we're probably going to start with something a bit more simple. But hopefully by the end of this video, we'll have gone from Lexing, simple parsing, simple type checking, and then some interpreting. And by the end of it, I'm thinking we'll have something like 4, 5 plus print, and that should work. And then maybe something a bit more interesting of like 1, 2, 3 print apply, something like that, or for each. We can change our minds as to what this keyword is going to be. Nothing is set in stone. This is all just like in my head. So I think we should start with this really simple example, because we have just one type, one operator, well, I guess technically 2 operators, because this is an operator, but this should keep us busy. So, and also, you may have noticed, I'm going to be doing this in Rust. I am not a Rust developer or even good at Rust. So if you're someone who like is good at Rust, this is going to be painful. I'm going to try and do this properly, but I make no promises. So, well, let's just start here, and we can build it as we go. So I'm just going to grab a drink, and then we'll get into it. All right. Cheers. It is a Friday evening, by the way. This is how I spend my Friday evenings after doing my day job of programming all day, is programming some more. But why not? This is fun. I have a Italian Pilsner or something along that lines. Oh no, this is a Taiwanese Pilsner. Very interesting, very nice. So how are we going to do this? So I'm thinking we start with the Lexer. So the first thing we want to do, if we move this over to the side so we can see what we're trying to build. If you've never tried to build a compiler before, I really recommend it. Like, it might seem like a really daunting project, but I promise you it's actually not that bad. It's the kind of project that, like, you can take it as, or you can, as I say, you can take it as deep as you like, but that might get me demonetized. Not that I'm monetized at all, but, you know, a man can dream. You can kind of, like, take it as far as you want to. So this is why I'm saying, like, we're just going to compile this, or we're just going to interpret this. We're not actually going to compile anything yet. Also, you know, this isn't going to be, like, highly optimized or feature complete and, like, capable of compiling, you know, being even Turing complete yet. Who knows? There might just be some things this language can't do. It doesn't matter. I'm making this for myself. So it's a really fun kind of project, and also it's the kind of project that, like, if you program, you already kind of, it gives you more of an insight into what you're doing, because, you know, you interact with a programming language all the time, and it kind of demystifies how it all works. So if it's something you've never done, sorry, my chair is incredibly loud. If it's something you've never done, I really recommend it, and I hope this gives you the confidence, and it kind of demystifies how to start. I've toyed with making compilers before, and none of them have ever got, you know, finished. But every time I do it, I feel like I learn a little bit more. And so I'm hoping that this is going to be, you know, a good way of learning something a little bit more. So I've been yapping for, like, probably 15 minutes, and I haven't written a single line of, like, actual code yet. I've written, you know, this. So let's begin. I did also watch back on the footage before I went and got a drink. I noticed my keyboard is really loud, so I'm going to try and keep that down. But it is a mechanical keyboard, and my microphone is, like, right next to it. So, yeah, not really much I can do. But we should start. So the first thing that we do with a compiler usually is we tokenize this. So rather than feeding these raw characters into anything that actually constitutes the language, we need to break it up so that we have, you know, a 4, a 5, a plus, and then this print. And a good way of doing that is, you know, splitting it on the white space. But the way I like to do it is sort of like having a cursor scan through until it grabs something. But we're going to start with enum of what kinds of tokens we have. So here we just have an int literal. I'm going to turn off. How do I turn off this stuff? Damn, it's really annoying. Because I'm trying. This is the thing about all this AI coding, is I feel like unless I'm just completely handing control over to it, it's really annoying. Because I'm trying to think through something and suddenly it just spits out a bunch of code that I now have to, like, switch what I'm thinking about and be like, oh, what is it? Like, does this make sense? Normally on IntelliJ there's a little copilot fella at the bottom. You can tell him to shut up, but Rust Rover doesn't seem to have him. So whatever. Let's just keep going. We're gonna have a int literal, and I'm gonna let's use a U64 for this, or maybe yeah, we want to have negative numbers. Let's have an I64. So we have an int literal, we have a plus, and we have a keyword, and that has a string. And this is probably where the Rust people are going to start screaming, is me using a capital or a string instead of a stir. I just don't like lifetimes. I will try and deal with lifetimes when when this compiler grows, but for now I just want to get something done, so I don't want to think about lifetimes. I understand they're very important, but right now I do not care. So these are the kinds of tokens, but I want to have some reporting information about where a token is, because later on, if we're interpreting or compiling this, this is an error, because we're going to reach the plus, and there's not going to be two values for it to pop, and it's not really helpful if the compiler just fails, because if this was a huge program and it failed, I wouldn't know where to look. So I want to have some location information associated with a token. So we're also going to have a struct, well, we'll get there, copilot, lock, and this is just going to have, well, actually we're going to have a span. I think a span makes more sense. You're very close there, copilot, but not span. We're going to have a start. So I don't mind that. I don't mind it when it sticks to one line and then auto completes that. We're going to have a start, which is the offset from the start of the file where the token begins. So this is 0. This will be 2, and you can see it at the bottom. Yeah, but it's normie indexes. So this is 0. This is 2. This is 4. Sorry. And then also has a length. So, these are all length 1, but this is length 5, and from that you can compute where a token is and how long it is, and then what that then enables you to do is have a really nice user experience where you can then take that information, take the source code, find the span in that source code that is causing the error, and you can just print to the terminal that line, and then you can locate underneath it and do a squiggly line, like how Rust, when you compile Rust, you get those really nice terminal graphics of you bloody idiot, you forgot to borrow this. Now you've fucked everything up and everything's on fire. I think we're far enough into the video that I can start saying fuck. Anyway, again, been yapping for probably 20 minutes now. I've written 14 lines of code if we get rid of this new line. So a token, for now, I'm thinking has a kind and a span. I think later it might make sense for me to also have text, because for printing out nice errors. If there's an unexpected token, it's nicer to print out the text of the token rather than the token kind name of it. But I mean, you can kind of get that without carrying that information around with every token. But again, we're just memeing around here. So that is pretty much all there is to it. So I think parser. Okay, I figured out. Turns out it was the other option. If I trigger him, oh, it lied to me. I went into I said disable multi-line suggestions, and here it is, give me a multi-line suggestion. Oh well. So, like I said, we're going to have a cursor, and we're also going to have some input, which is a string. Should it be a string? I can feel the Rustaceans screaming at me that it should be a stir, but we can change it later. So, the impl for the Lexer, what do we want? Well, we want something that, a function that, that's probably a good place to start. This is what I mean about the suggestions. They just sidetrack you. And then we just want to return Alexa with the input and a 0 cursor. Okay. What we actually wanted was a next function, like this. So this will, it's mutable, yeah, because we're going to advance the cursor and return a token. And actually, there were two other tokens we should probably add, at least one. There should be an error if we don't really know what the token is. So like if we had a minus, which we don't support yet, that will be an error. And an EOF, which is end of file, so that things later on know that we're done lexing. Yes. So we want to have a look at what we currently have. So what would be nice is a peak function. It doesn't return a token, it returns a character. And yeah, but from memory, nth reads from the start. So really what we probably want to do is slice the input. Can I just index it? Or is that something that only a stir can do? Cannot be indexed by usize. Is that because it's a usize, or is that because it's a string? Yeah, I think that's it. You know what? We're just memeing around. Let's just chars nth cursor, and that's an option. So yeah, this will be an option of char. So the first thing we're going to do is or C self peak. We're not going to unwrap. In fact, we should match on this. If we have some C, we'll sort that out in a second. If we have none, well, that's where our EOF comes in. So we'll have a token with token kind EOF, and the span, well, our offset. What are you complaining about? Oh, sorry, it's not offset, it's start. I think I think I prefer offset to start. So we'll call it that, which is our cursor. And the length is 0. It doesn't really make sense for it to have any length, and I think this is fine. Okay, so in here we have a character. We don't know what kind of character, so we should probably match on the character. So the first one we should probably handle is the plus. No, I think the first one we should handle actually is unknown. So we should return a token of kind, or error, not unknown. And I think actually it makes more sense for this to be a character, because, or we'll have it a character for now, but I feel like, you know, if this was like this, is that 4 tokens? Or, you know, these are 4 pluses, but, you know, if we had like a token that, or, you know, something that we probably won't have as an actual token, like $, is that 1 token which is $4, or is that 4 tokens that is $1? So let's say that's 4 tokens that's $1. So error of C, and it should let me copy that because it's a character. And so we have offset of cursor, self cursor, and a length of 1. Ooh, that's a spicy suggestion. You're quite right. It might not be 1 byte long. This opens up a bit of a can of worms. Because, yeah, a character might not be 1 byte long. Like, if you imagine I put a Chinese character, or, you know, a Japanese character, or one of the high-up Unicode characters, that could potentially be multiple bytes. But it's only 1 character. So, that's a good suggestion. Okay. You win this one. Go buy it. Okay, So we've handled error. We now want to handle plus, because that's the easiest one. Let's see, how much can Copilot help us? Plus. Span. It's kind of the same as this, isn't it? It's kind of the same as that. And then, yeah. I wonder if we can factor that out later. We can think about that later when we have more tokens and this becomes quite large. But for now, that's good. So now we kind of have an interesting thing, because what we could do is, match on like 0 to 9. I feel like is a good idea. But we're not going to return just that one digit, because this could be 45, 55. So we want to keep consuming characters until we hit something that is no longer a digit. Because, we could not put a space here, and that should still be a valid program. So we need to consume characters until it's no longer a digit. So let's introduce a, what should we call it? Lex number. It'll be oh, there we go. It would be self. I'm just gonna use the mouse. Screw it. Self. Can't even use the keyboard. Lex number. And this would, yeah, this is infallible. This will either return a number or nothing, or or an error if something goes wrong. So Lex number. How is this going to work? So this is inside Lexer, so we have the input and we have the cursor. The cursor, that's something we've forgotten. So we should not return immediately. We should save that, and then self cursor plus equals token span length, and then we return the token. Otherwise we'll just keep parsing the same, or keep lexing the same character over and over again. So we're currently on a number. So we want to save where we are. So let's call it offset first, because then we're going to use that when we build the token. And then we want to keep peaking. So let C equals self peak. Yeah, we want to peak, and we want to match this. So we have some C and we have none. If it's none, we should return what we have. So how are we going to do this? Because we can't have none on the first like when we enter this function, because we've entered it on a digit. So this would be, if we've ended on a number and we've now hit end of file, there's nothing to peak. We should now just take everything that we've just skipped and return that as a number. So how are we going to do that? Let's slice. Yeah, let's slice what we've got. So we'll say number is self input offset till self cursor. Parse it in a second. Can I not do this? Cannot move. Can I do that? Aha, got ya. Yeah, and then we maybe do want to parse that. And let's say that we know that it's going to be a number, because every time that we peek at the next character, if it's not a digit, we end. So if we put this back to this, you know, if it was this, as soon as we peek at that plus, not a digit anymore. So we have a number. It is an I64. It's a reference of I64, but that's fine. Yeah, we can just dereference that, and I think that will just copy it, which is fine because it's just an I64. And we can, the length. Yes, so this is why we probably don't want to do that immediately, or I guess? No, I guess it's fine. Because we can just take self cursor minus the offset, and that is our length. Cool. So that's in the none case. So in the sum case, we want to, we don't need to match, actually. We can just say, let's see, what is it? If C, is digit? Is ASCII digit. What's the difference? Yeah, so is digit, yeah. Let's only handle, yeah, so I guess the is digit with the radix, yeah, that's saying like what base is it in. So that's kind of handy, actually. We can have hexadecimals really easily then. We're not going to. We're not going to worry about that yet. We're just going to do an ASCII digit. If it's an ASCII digit, fantastic. We will... Yeah, we need to have a bit of a while loop here, don't we? So if it's an ASCII digit, we just self cursor plus equals 1. If I could type. So we have that. But we need to return something. So this kind of needs to be in a while loop. So if I say let mute C equals self peak, while, let's say C is sum and C is, unwrap is ASCII digit. There we go. We do this. This then we'll have to return because we're now in a block. And then this, we can just to do it. That should be okay. That should return, but it's not. Do I have to be explicit? Then maybe it will tell me why it's unhappy. This needs to be mutable as well. But that doesn't seem to be the cause of the problem. This is something that really gets you with Rust, is because this is an expression, or like all these things are expressions. Sometimes it gets a bit, well, I mean, it doesn't get confused about what the return type should be, but like, you know, you haven't quite finished implementing something, so it doesn't quite get the type right, and then you just get messed up. So something about this. So we're returning this. The none case returns a token. This should to do. But why not? Is it just because if yeah, it's because if the while loop, if this is false, we're never going to return anything. Okay, all right. So I don't need this. Well, I do need that, but we're going to get rid of it. So if it's an ASCII digit, we increase and we continue. If it's not an ASCII digit, then we're done. And we do the same thing as here. Oh, I'm silly. We should be matching on C, so we should increase the cursor and C self peak to an immutable. Because I've there. Unreachable. Why is this all unreachable? Really got myself into a pickle here, haven't I? Okay, I had a bit of a think with the camera or with the recording off, just so you weren't staring at me trying to solve this. I think this is simpler. We save the offset while we have some character that is an ASCII digit. Increase the cursor. As soon as this becomes false, either we've hit the end of the file or it's no longer an ASCII digit, and then we slice out that bit of text, parse it to an I64, which we should be able to do. That will fail if it's too big, but we don't have to worry about that yet. And return a token. There we go. Easy. So, that's that. And then we have this, which is really similar to digits. So this is yes, is an A to Z or capital A to Z. No, I don't. I think it should be a. Let's move this down here, and let's say match C as X if X is alphabetic. And in fact, we can actually replace this with X if X is ASCII digit. And I think that's a bit better. Maybe this is implemented the exact same way. Yeah, it's implemented the exact same way, but it reads a little bit nicer and it matches this. And we can just say self lex keyword. And later on we might have identifiers which will use the same system, but for now we only have keywords. And the only keyword we have is print. So maybe instead of keyword string, we should just have print keyword. Later on, this will be a function call, I would imagine. But for now, we should just have it be a print. So let's implement lex keyword. And it's going to be very similar. So while we have sum is alphanumeric. So I got sniped by a cursor. I was literally just about to explain this. We want it to start with an alphabetic character or an underscore. That's a very good point. So if you go back here, if it's alphabetic or... Oh, my keyboard is in the wrong language. I have an American keyboard, annoyingly, so I have to put it to US. I know I'm a traitor. X or X is an underscore. So that means you can just start a keyword or eventually an identifier with an underscore. But also, you know, a keyword or an identifier may have numbers in it. You know, we want this to be all one keyword or one identifier. So once we've got over this initial character being either an alphabetic character or an underscore, we're free to just consume if it's alphanumeric or an underscore. As we do that, we no longer have to parse it as a integer. So let's say let keyword equal that. And then we want to match on the keyword. So maybe we do want error to be a string. Because if we don't know what this keyword is, we want to report that. So we want to say this is an error of the keyword, and then I don't believe we have to do that. In fact, yeah, let's just string it. I'm sure we shouldn't do that, but whatever. And so that's probably broken this. Yeah. How do you... You can just do that. That's so much better. That's something I always forget how to do in Java, which is like the language I've been programming in for like 10 years at this point, is how do I turn a character into a string? And in Rust it's just dot to string. Beautiful. Okay, so if we don't know what the keyword is, it's an error. So now here we can start implementing our actual keywords. So currently we only have print, and we don't need to have curlies. And this is print keyword. Good. I think we can probably get that out of there. Good. And then yeah, and now we can shorthand initializer, and then that's nice and tidy. There's one more thing missing. Do you know what it is? White spaces. And would you believe it? It's very similar to those last two that we've just implemented. So, before we start peeking at characters, what do we want to do? We want to skip any white space. We want to skip any white space. And then if that takes us to the end, so if we have white space at the end, if that takes us to the end of the file, we will hit the none case and we'll return an end of file. Very good. Okay. Once this is all working, we should test all this out and see if any of that is true. But probably this is the easiest one to copy. In fact, let's put this at the top because it's going to be the smallest one. So skip white space while some peak if C, let me guess, does it have it? Is ASCII white space. Cursor +1. But this does not return anything because there is no white space token, so we don't even need to save the offset. And that should be it. Yeah. I think, what is that, like maybe 45 minutes in? We have our basic Lexer. So let's run it. Okay, so how do we read a file into a string in Rust? Well, let's go to our main. For now, let's just hard code it as it'll be resources foo.do is our file name. And if I say input, why even try and think when the machine's... I don't know why in my head I was like, oh, I need to say I need to try and figure out how to do this as I'm speaking. Don't have to. Right, go on then. What's next? I'll get you started. I guess it's while let. Oh, it's not really let, is it? I guess it is. While let. It's not really optional. We need to make this mutable. Yeah. While let token equals at next, push that. Well, we also want to say, if token kind is EOF, we don't really want to import, we just want to say token kind EOF, break. It's probably not the best way of doing it. We'll make it partial eq. We don't want to implement, we just want to... I never remember the syntax. What is it? Derive partial eq. There we go. Yeah, we probably want to do loop, but yeah, we don't want to do that. And then why don't we just print line the token? So we need to probably inherit a few things on all of these. Value moved, sure. We can print before, even though it's exactly the same. I understand why I can't do that, but it's very silly. Debug, and then we probably want partial eq on all of these anyway, so that we can equate them. Yeah. And that should be it. Okay, let's actually run this, see if it works. No. It seems to be stuck in an infinite loop. Very good. Why? Let's put a little debug. So here, print line self cursor. I can never remember how you do that properly. Always do it like that. Very interesting. We never get beyond 0. Did I forget to increment the cursor somewhere? So we skip the white space while... Yes. This should be an else break. So should this. And so should this. Let's try again. There we go. And we no longer need to print the cursor. So let's get rid of that. And there we go. We tokenized 4 tokens. And it took us about an hour. Okay, let's try and go a little bit faster. So in the next hour, we're gonna have what would this be? 90. We're gonna print out 90. Okay. Very good. Let's now parse. So I think we'll have it all in this file for now. So what we want is operations. So for an enum op kind, what kinds of operations do we have? We have plus, correct. But we also have push. And for now, we're just going to have it like this. We're just going to push integers. In fact, this could be push int. You push int, and we'll have print. Those are our 3 operations. From 5 tokens, we'll have 3 operations. So if we have, if we also have a struct op, which has a kind and a span, because very interestingly, a operation can be multiple tokens. So if we go back to our original example we started with, where we had an array, this is a lot of tokens. We have an open square, we have this, so we have a push in, we have commas, we have and then all of this, and then finally we have a close bracket. This is all one operation, which is going to be push array or push list, something like that. But it's going to be wider than a single token, so we need to know its span. So we need to be able to construct spans from other spans. So we're going to get to that. But that is an op. So we're also going to have a parser. I think we're going to do this eagerly. This is probably not the best way of doing it, but we're just going to eagerly lex the entire file, and then we're going to parse it, and then we're going to interpret it, which I think is fine. And then, yeah, we'll have a cursor. Why not? We'll see if that even makes sense. So if we import parser, well, no, it's not going to be like that. We're going to init it with the... Oh, come on, that's not what I want. Okay, all right. Yeah, that's what I want, but I want it... Yes. Okay, that... Yeah, I saw this and I thought that was this. Silly me. So that's that. So we also want next, which is takes a mutable pointer to itself. It doesn't return a token, it returns an OP. But this could fail. You know, it might not make sense. But let's not worry about that, because right now it's very simple. We have one token to one operation. So for now, we can get the current. Maybe it makes more sense to not have to worry about that and just have parse. No, it does make sense. Let's have parse OP, movable self. Because I was going to say it makes sense to just like parse it all in one go, but we still need to have a function that can parse it one at a time. And I think it should return an option of op, yes. So, I wanted what you had before. Yes, that. If our cursor has gone over the number of tokens, that is none. And then we want to match on the kind. And then this is very easy. What is this? Go away. So if you have I64, that is OP of push int, and then we just hand the I64 to it, and the span is the token span, and it's probably going to complain about that. Oh yeah, this has to be some. In fact, let's say no, some OP. Yeah, cannot move. Do that. Do that. No, of course that wouldn't work. Maybe we have our first clone. Oh, we can't do that because token kind doesn't have clone. Maybe it makes sense for token kind to have clone. And then these need clone. Maybe that's fine. These are very small. Just this one. This is where string starts to get a bit poopy. And then it still doesn't work. Still doesn't work. Got him. There we go. There we go. So, then we just do the same for plus, but instead of push int, this is plus. And then for print, instead of push that, it is print. Error in EOF, I think they should just return none. And that's parsing. That was way easier than Lexing. Granted, like we don't have any like multi-token operations yet, but we can get to that in another episode. Cool. Next, we want to type check this. So, for type checking, we need what kinds of types? Currently, we just have int. Later on, we'll have bools, structs, strings. Why not? For now, we just have ints. And I think, yeah, we don't need a void type or a unit type or anything yet. So we want. We don't really. We don't need to transform these into like typed operations. So I think we can just have a type checker struct which has a type stack. This is what I was saying before. Yeah, which is just a vector of these kinds. Starts empty, and then as we go through the operations, we push onto the stack when we see a push operation, and then we pop from the stack when we see anything that would pop. And then there we can see, you know, if we have a valid program or not. So we have that, we have OPs. Cool. Cool. So let's import the type checker. Yep, we want to init it with some ops. We probably don't want to init it with a type stack yet, though that will potentially be a thing when we come to do functions, because when you want to type check a function, if you say that the function takes in an integer, you want to initialize a type checker with an integer on its type stack to then type check the body of the function. But that's getting ahead of ourselves. So we have this, and then we just want to type check. Just like that. Not with a token though, we just want to for op in, oh, my Java is showing, in self ops. We don't really need to iterate it mutably. We probably want to take a reference to it though. And then we just want to match the op. We want to match the op kind. There we go. Oop. There we go. That's not really how I would want that to auto. There we go. That's what I wanted. Push in. We don't really care. Self type stack. Push. Type kind. Int. Easy. Plus. Okay. We want to match self type stack pop. If we have some int Gucci, if we have some other thing, not type stack overflow, but we will implement proper error handling maybe at the end. For now, let's just panic. Expected int but got this, and we want to implement debug, derive debug. I'm sorry, my Java is showing. And then the last case is none. Expected type kind int, but got none. But stack was empty. Yeah, this is unreachable for now. I think just to keep it happy, let's add another one. We don't have booleans yet, but that will probably be the next thing we implement once this is working. And then print just pops. So we just want to what do we want to do? Yeah, if it's something, we're good. And if not, expected any. In fact, let's not do type kind : : in. That's silly. Expected int, but got nothing. Expected int, but stack was empty. Expected any. Maybe we should have an any type at some point. Maybe that would be good. But for now, that's good. We probably we've written all this code. We haven't run anything in a while. So let's. So now we've got our tokens. Let's make a parser from those tokens, and while let sum. So yeah, maybe it does make sense for the Lexer to return an option. Maybe we'll come back to that, because that seems to be the pattern so far. So let's make a vector of ops, and then we just push the op. But let's also, not self, but print line, and take a look at our ops and make sure everything is as we expect, and we need to derive debug. There we go. So we should see push int 45, push int 55 plus print. Yep, we also need to derive debug on opkind. And then we're good. Okay, let's have a look. Oh, what did we not do? What did we not do? We did not increment cursor. Let's just do that. Because then when we parse like lists and things, that will then advance the cursor itself. But for now, we'll just do that. And there we go. Ooh, that's not good. Did I not save this? Why is that only 5? Interesting. Was that the token as well? Is that because the token is 5? I'm pretty sure that's the only reason why that would be the case. So if we print the tokens, yeah, something has gone wrong. Something has gone wrong with our Lex number. Let's take a look. So, while some peak, so we're here, we peak, and is ASCII digit? Yes. Advance. Is ASCII digit? Yes. Advance. But why does it work for 45? Not 55. Ah, I know why. I know why. If I was to change this to 56, yep, it chops off the beginning. It's the problem is in white space. So if it's ASCII white space, self cursor 1, skip the white space. So why does that cause a problem? Why does that cause a problem? If it's a white space, advance, peak. Maybe we should put a debugger in, because we can do that. I've had mixed experiences with the Rust Rover debugger. Sometimes it can figure things out, sometimes it can't. I imagine that's just because Rust is a bit more low level than like Java and stuff, which JetBrains are used to. But so we should get in here, Lex a number, self cursor plus equals token lang. So our cursor is there we go. We're advancing the cursor twice. We don't need that. We do need that. Is it off by 1? Is that what it is? No. Wait. Let me try it. Yeah, no. Because we Lex a number. We're incrementing the cursor. When we skip white space, we increment the cursor. When we do plus, we don't. So yeah, this isn't. We shouldn't be incrementing cursor, but we should be because we're peaking. That's a stupid mistake. That's very annoying. But why is it if we don't do that? Why do we get stuck on the 6? Why do we get stuck on the 6? So what do we parse? Oh, sorry, what do we Lex? Yeah. So we get these two correct. But then we seem stuck on this. Wait. That's the offset. I'm stupid. Oh, that was a stupid mistake. Yeah, okay. Yeah. No, it's exactly what I said. So yeah, we don't want to increment all the time. We only want to increment if it's a plus. But there's going to be so many other tokens like that, and it's only the ASCII digit and the alphabetic ones that advance the cursor themselves. So, what is the best way to do this? Is this the best way to do this? If it's int literal or a... no, because it's going to be all the different keywords. Okay. That's not a good way to do it. I think instead I should say let token equal token self cursor plus equal 1 token. Something's not happy about that. Do I just want... Oh, because I'm in a block. We'll just return token. Still not happy. Plus. Okay. There we go. And then it's not complaining about that, but I can... Yeah, I can just say token. Okay. And there we go. Okay. So now we have push int 45, push int 46, plus print. Okay. Okay. We're there. So now, if I take away that, well, actually, we don't do the type checking yet. Let's do the type checking. So we have our ops. And if we have a type checker, and we just type check, yeah. So if it finishes with exit code 0, we have a valid program. If we do this, program expected any, but stack was empty. There we go. And then, yeah, so this panics in the compiler. We really want diagnostics. So I think maybe tomorrow I'll record another bit of this and put it on the end of this video where we implement diagnostics. But for now, this is fine. If it's not a valid program, we halt compilation. Great. So now we want to interpret this program. So let's create a interpreter. And what does an interpreter have? So I think it makes sense to have values. Yeah, like this. So we'll have an int value with an i64. And for now, that's the only value we're going to have. But this is why I want it to be interpreted rather than compiled. Because when we get to lists, and especially functions, that's where things start to get spicy. Because we might have func, or I guess quote, or I can't remember what they're called. But a function. It'll be something like that. It'll be vec to vec, and then a sequence of ops. Or no, it'll just be a vec of op, like that. But we're not. That's way ahead of us. So we have that, and then the interpreter has a stack, which is a vec of values, and the interpreter, yeah. Yep, that's all good. So we just want to interpret a vec of ops. So for op and ops, we want to match the op kind, and if it's an int, we just want to self stack push a value of int, and we shall just put, yeah. Kind of weird calling it i64. I think we should call it value. Although I guess it's value. I like value. And in fact, I think I should go back and change that for the ops, like this. Yeah, I prefer value, because then you can have the same thing for balls, and then you can have better pattern matching. Yeah, we'll see. Plus is very easy. We've type checked this program, so we can be a bit more reckless with popping off this type stack, or this stack, because we know it's going to have values because we've type checked it. It's a valid program. So we just want to self stack pop unwrap, because we know there's a value. So A, let B, and then this is where things are going to get interesting. Self stack push A plus B. But A and B are values, they're not ints. And what I could do is say, I'll let value int A. So you could do this, and then you could have a value int of A plus B. And for now that works, but what if you want to add strings and concatenate them? That should be valid, because this isn't C. You should be able to. I don't know, you can plus strings in C. What am I saying? That's something you should be able to do. Or you should be able to add integers and floats. But we're saying, oh no, this has to be an int. So in future, what we probably want to do is like implement add for value, and then there we can match on all the different possibilities of all the different combinations. I think that's what we will do in future, but for now we only have integers. So, in fact, does this only compile because the only kind of value we have is an integer? If I add bool, this no longer... Yeah, refutable pattern in local binding. Aha, there you go. So we will eventually have to implement add for value. But for now it's fine, because we only have integers. So we have this, and then, yeah, we can do that. And then we just want to, we don't want to push it back on. We want to print line A. We need a format. Bam. And I think that's it. So it took us like half of this episode to just write the lexer, and that seems to be the buggiest part of this. The rest of it was just pattern matching, essentially. So let's get rid of all these debug prints. Let's not get rid of them completely. Let's just comment them out, because as we add more, other stuff is inevitably going to go wrong. So if we have an interpreter, and is this not? No, because this is very interesting. I hadn't even considered this, but we don't initialize an interpreter with ops. We could, but then that makes the interpreter not reusable. And I haven't talked about this, but something I really want is a sort of like a REPL for this language. So you will run the, you'll run do, and then you can type in a line of do. And what it will do is it will lex, parse, type check, but it happens more leniently. Well, no, you still need to have valid stuff on the stack, but it can leave stuff on the stack afterwards. And actually, we haven't implemented that, because I was thinking a valid do program should end on an empty stack, but we can sort that out later. So if I wanted, I could have leftover integers on the end of the stack, which you probably don't want. That usually means you've missed something. But anyway, if the interpreter is reusable, what you can do on every time you enter in a new line in your REPL is just pass those ops to the same interpreter, and it will have the same stack. And it will have the stack left over from your last line. So if you pushed a bunch of integers on, it will have that, and then you can say, oh, type print, enter, it'll pop off from the stack, and it will print the first value. Okay, that's very cool. So, interpreter, interpret ops. Why doesn't it like that? Used after being used, or after moved, yes. So the type checker doesn't actually have to own the operations. And in fact, the type checker doesn't need to have the ops at all. It's the same thing. You want this to be reusable. So we don't want to do that. We just want a reference to the ops, and so does the interpreter. The interpreter doesn't need to own the ops. So this is a what would it be? Would it be a can I do vec of op? Is that owned? No field ops. Oh, yeah, because it's no longer. Can I do this and then that? Yeah, I feel like this is wrong, but I don't remember how you're supposed to do it. Expected vec of op. Yeah. Get rid of that. Get rid of this. And so now we want to type check the reference to the ops. There we go. And we want to interpret a reference to the ops. Yeah, and that fails because we haven't passed this by reference. Okay, So, if I have done everything right, when I run this, it should print 100 maths. Yeah, 101. It's just that easy. It's just that easy. And then this isn't hard coded, so I can just do 13, 14 plus 7 plus print. And that prints 35, which is correct. Because, yeah, 18, 28, 35. Yeah. So, we have a programming language. It's a very dumb programming language, where the only thing you can do is add numbers and print things. But it is a programming language, and I can have a new line, and I can say 5, 6 plus print, and it will print two things. And I can do, 6, 2 minus print, and it will break. Oh, it hangs forever. How interesting. Why does it do that? Oh, I guess because it never gets to end of file or something? I don't know. Oh, it goes to none. This should probably report an error. But we'll get to that when we do diagnostics. So let's add minus. Why not? So, getting ahead of ourselves. We need to add the token first. So if we go here, and if we add minus, and we find where we do plus, I can already see this is going to be repeated a lot. This. Can I make a method out of this? That was the wrong combination of keys. There we go. Extract function, lex token from the char, and then it should. I want to say token kind plus. So if I go here, token kind. Let's just say kind, because then I can just do that, and yeah. So don't need to do a comma, and then this is just self. Oh, we don't even need the brackets. Look at this. Comma. There we go. And this is minus. And then, because we're using exhaustive matches, this then fails. So now we bring in the minus OP. So if we encounter a minus, that is op kind of minus. When we type check an op kind, it's actually the same as plus. So we don't even need to do anything special. We can just say op kind minus is the same. And I kind of want to do a more interesting or a more resilient way of type checking where every OP can define its signature, and then you have some generic code that just takes in an OP, says, okay, what's your signature? You take 2 ints and you return an int. Okay, pop, pop, push. I've just noticed that this is wrong. Yeah, this only pops a single int off the type stack. Because it should be this. And so it should be like that. Then you either have this. Yeah, see? This is why having, let's do it like that. A B, but got a B, yep, or none, none, and then expected in, but stack. So yeah, that's yeah, whatever. So that's the better way of type checking it, but there is an even better way where the ops will say, okay, well, I take an in and I return an in, and then we don't have to implement it like this for every kind of operation, especially when you get to like stack operations like push, like pop and swap and rotate and stuff like that. So, and now we do the interpretation, which is just that. So this is why I want to implement like add and sub and stuff, because the more of these we do, as soon as we add another type, this entire thing is just going to fall to pieces. But for now, also the ordering is very non-intuitive, at least I don't find it intuitive. I believe this is going to be 2 minus 6. I might be wrong. This might print minus 4. Otherwise it will print positive 4, in which case, yeah, it's very unintuitive to me. Let's find out. Damn. Expected int, but stack was empty. Ooh. Why was that? Expected any, but stack was empty. Ooh, do you know why? Do you know why? Again, this is why I need to implement the signatures, because this is still wrong. What do you do if you have two ints? Well, first of all, you learn how to type. Self, type stack, push int. You have to push an integer back onto the type stack. And it's minus 4. I was right. It's minus 4. Okay. So, why don't we just implement the rest of the arithmetic operations? So what do we have? We have star, we have slash, and we have percent. I suppose we could do mod or remainder, whichever one it ends up being. And now this is super simple. And now this is the kind of stuff AI is good for. Is the boring stuff I don't want to type. Don't think for me. Do the shit that I don't want to type. So now, let's see. Now we just want start. So actually, yeah, we need some new ops. So we need multiply. It's not the 70s. We can have the full modulus. Modulo. Yeah, it's not the 70s. We can afford the space in our compiler to use full names. So star is multiply, and then just copy paste slash. Whoa. Slash is divide, and percent is modulo. Alright, and then the type checking is just op kind multiply, op kind divide, op kind modulo, will it? Yep, there we go. And then interpreter. Okay, this one's a little bit more annoying. Multiply, divide, modulo. Okay, so we can do 4, 5 times 3 divide 10 plus 2 mod print. So what's that? 20 divided by 3 is... what would 20 divided by 3 be with an integer? But it would be like 6. Yeah, 6, 16, 0. Should print 0. I'm wrong. I think it did 2. I think the modulo goes this way round. Yeah, there you go. So that's the thing about stack-based stuff, is the order of operations you do have to be kind of careful, especially with the non what's the word, commutative operations like divide and subtract and modulo. But I think this is pretty cool. We have a pretty cool system. And you know what? Before I finish it for today, why don't we do a little bit of stack operations? Why don't we do swap keyword? Let's implement swap. This is very interesting. So we need new keywords. So print goes to print keyword. Let's put it above because it comes before in the enum. Swap keyword. So now we need a new operator kind. So we have a swap op. A swap op. Swap keyword is a swap. So how do we type check a swap? We don't need to match. Oh, we do. Yeah. It's basically the same as print, just twice. So some A, some B. This is horrendous code, by the way. This is what, like, as soon as I implement signatures, I know I keep saying it, as soon as I implement signatures, this is going to get a lot better. So A and B. So B was on the bottom. So we pop off A, and then we pop off B. So we want to push A and then push B. It's not quite right, is it? So we want to push A, and then we want to push B. There we go. And then we have a new op to interpret. So op kind swap. So this we don't actually need the type. It can be any value. So we pop A, we pop B, and then we push A, and then we, come on, Copilot, we push B. There we go. So let's leave that one there, and let's be a little bit more interesting. Let's mod it with 3, just so we don't get a 0. So yeah, we have 1. But let's say I don't print the -4. And I don't print the 1. And instead, I swap them, and then I print them. So it should go 35, 11, 1, -4. It didn't do it. Why didn't it do it? Because we should be swapping. We pop A, pop B, push A, push B. You're making me look like a fool, Rust. You're making me look like a fool. Let me try a simpler example. 1, 2, print, print. Yes, because we print the 2, and then we print the 1. Ah, ha, 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 very funny. It did swap them. I was just printing them in the other order. Okay, so, because otherwise this, first of all, it will print and pop the -4, and then it will print and pop the 1. But if I do it like this, we put the -4 on the stack, we put the 1 on the stack, we print the 1, we print the -4, like so. But if we swap them, it goes back to the original order. Okay, one more operation, because I think we need, let's put it above so it's alphabetical. We need to square, because that's how we started, so I think that's how we're going to end, is squaring a number. So, we want to add a new keyword. Let's get this out of the way. So we have dupe. So the operation is dupe. So if we have a dupe keyword, we are doing a dupe. If we want to type check a dupe, so we want something on the stack. So we want this. And then we just want to push. It's obsessed with pushing balls. We'll get there. We'll get there. We want to push an A, and we want to push another A. But because we're in Rust, we need to clone the type. So we need clone, which is fine because it's just an enum. There's no big data stored there. So we pop an A, and then we push 2 A's onto the stack. And then to interpret that, why we just do the same thing. And again, it's generic. We don't need to force it into an int. But we are also going to have to clone the value, which again, I think is fine. Not debug. I mean, it's probably useful to have debug so we can like print values in debug. Okay, so we have all of that. It's now 5 dupe star print 25. There we go. So I think that's pretty good. I think that's a pretty good start at do. So I think I'm going to end the recording here, and then I'm going to see about doing another session tomorrow, whether I add it onto this video or as a separate video, depends how long this one is. We'll start to clean up. I think next time we should sort out the type checker. This is disgusting. Like, this is not gonna work once we start getting more complicated and adding like functions and things. We need to add signatures. But also, like, this is also just, that's not right. We need a proper like diagnostic system. And we also need to not fail the compilation, or rather, we don't need to halt the compilation at the first error. We want to gather all of the errors, and maybe one per line, just so we don't like, well, I don't know, we'll see. So that you aren't just like doing it one error at a time, you get to see the whole thing. I think that's probably a good next step, and then we can start doing more complicated operations, like pushing lists, maybe pushing functions, and maybe things that take functions and lists and applies them and stuff like that. But that'll have to be next time. So, I mean, if you made it this far, thank you very much. I appreciate this is very dry, but also I feel like there's a certain type of nerd. Like, this isn't going to get thousands of views, but there's a certain type of nerd that's just like me that loves this kind of stuff, or is someone who's just like curious about how do you even make your own language? How do I get started? And it's just as simple as just like this. You just write a made up language, and you just write code that turns this into that. So yeah, if you made it this far, thank you. Please comment. This is my first time doing this sort of thing, so let me know what you liked, what you didn't like, anything you want to see, any ideas or suggestions for do, because like I don't know where this is going to go. Yeah, so thank you very much. I hope to see you again. Like, subscribe, comment, all that good algorithmic juice. I'll see you next time. Bye bye.